I'm going to talk about, what is my professional passion in my life. It's texture in metal alloys. And when I say metal alloys, I mainly mean steel and aluminium. These are metals with cubic crystal structure. So, of course, what I'm going to present you did not do it on myself. This is the work of many different people, of which I make here a list, and probably my apologies to those I forgot. There are others also who contributed. Now, why we should be interested in texture? One of the reasons is, in my view, there are main three reasons, and one of the probably the original and some would say the most important reason is that texture is a major source of anisotropy. So material properties in generally they are anisotropic. It means that if you measure, for example, the Young's modulus in a sheet steel along the rolling direction or along the transverse direction or under an angle of 45 degrees, you will find different values. This is what we call anisotropy. And texture by itself, the presence of a crystallographic texture, it is a major source of anisotropy. So all properties with crystal, you could say that if you consider a single crystal, and if you have a material property that is anisotropic in the single crystal, then by extension it will be texture dependent in the polycrystalline aggregates. So actually, in first approximation, you simply can say that the polycrystalline aggregate is just the average behavior of all of the single crystals. And if something is anisotropic in the single crystal, then it is texture dependent in the polycrystal. So many properties of materials are anisotropic, not only the mechanical properties such as yield strength, hardening, or yield locus, also a wide range of physical properties like elasticity constants, thermal dilatation, surface energy, chemical or electrochemical properties, and magnetic properties. So all this can be subject of study in texture-dependent phenomena. This is one aspect. Now, another good reason why we can take a close look at the texture of a material is the fact that texture can serve as a tool for acquiring a better understanding of the metal science or of the mechanism controlling the so-called solid state transformation. Sometimes I call texture is a metallurgical probe. What do I mean with this? Well, if you deal with metals, if you make them, if you process them, if you use them, they are bound to happen structural transformations. For example, you go from the liquid to the solid state, you go from an initial phase to a final phase. In steel, for example, you have a famous austenite to ferrite or austenite to martensite phase transformation, but you also may have plastic deformation, you may have recrystallization, grain growth, whatever. So all these are called solid state transformations. And there is a whole, there is a lot to say about these transformations. So many things we understand, we have a good knowledge about, but still many things we do not yet understand. And then looking at it from a crystallographic point of view can help us to understand these phenomena. So it means that if we look at the texture, we can have a better look into the physics, into the basic understanding of what is happening during these solid state transformations. So you cannot have, for example, a complete theory of phase transformation without knowing also the crystallographic aspects of this theory. Yeah, so it has taken scientists a long while, in fact, until to get a complete description of texture. So nowadays, normally we represent the texture of a material in Euler space. So, for example, this is the 0-90 degrees box of Euler space, and each point in this space represents a crystal orientation. For example, this point here is the cube orientation, this point here is the Gauss orientation, and you also may have not single orientations, but so-called, just a moment, but you may also, have texture fibers. So these are the lines. So for example, this blue line here is the theta fiber. These are all the orientations that have the 001 axis parallel to the normal direction of the sheets. And this is the gamma fiber. These are all the orientations for which the 111 crystallographic axis is parallel to the normal direction, and so on. And this is the beta fiber. The beta fiber is not so easily to characterize, but it is very important for the deformation texture in FCC materials. We still will encounter this fiber later. So, for example, fortunately, if we're dealing with rolled products of steel and aluminium, we do not necessarily need to consider the entire three-dimensional Euler space. We can be quite happy just considering a limited number of sections, like, for example, this is the phi2 45-degree section. It has a number of very important components. So you recognize here this blue line. So what we are looking at here is this section at phi2 45 degrees. Can you see my mouse? Yes. So this section is repeated here. So this is the cube component. This is the rotated cube component. Here, this is our famous gamma fiber. Excuse me. So this is the copper component, 112 minus 1 minus 1, 1. In the phi2 45 degree section, we have another very important component. It's the S orientation. And in the phi2 90 degrees texture, we have the Gauss and the brass orientation. Mind you that because of multiplicity, this Euler space, it's a kind of it's an odd thing. It looks a little bit like a mirror palace. If you have ever been to a fancy fair and you enter the mirror palace, you can see yourself in many different corners. Well, the Euler space is a little bit like that because, for example, the Gauss orientation, we do not only find it here in the phi2 90 degrees section, but we also find it here in the phi2 45 degrees section. This has to, I don't have time to go into this detail. This has to do with symmetry, crystallographic symmetry. This was basically for FCC materials, aluminium, copper, nickel, gold, silver. For BCC materials, so iron at room temperature, probably the most famous, but also tungsten or molybdenum. If you roll and anneal such a steel, such a BCC material, actually we can do with the phi2 45 degrees section. This is only the phi2 45 degrees section, and it has the famous, this fiber here, this vertical fiber, we call it the RD fiber or sometimes also the alpha fiber. So you can see all the components of this fiber, they have one orientation in common, one direction in common, namely the 110 direction. This is the 110 parallel to RD fiber. And this is the gamma fiber, and otherwise also known as the ND fiber. And all these are points on this fiber have the 111 crystal plane parallel to the rolling plane. So this is the 111 fiber and this is the 110 fiber. For example, if you want to have a good deep drawable steel, so this is very important in steel manufacturing, then you want to have a texture that is centered around the gamma fiber. So that's actually what you want. We will come later back to this. Okay. Good. So now let's have a look at the different solid state transformations and how they may affect the texture. For example, probably one of the best known, most documented phase transformation is the FCC to BCC phase transformation in iron, in steel, in low carbon steels. So where FCC is the high temperature austenite phase and BCC is the low temperature ferrite phase. Now, if you have a ferrite and lattice, there is a certain crystallographic orientation relation between both. And there are various different orientation correspondences that are described in literature. One of the earliest was the Bain correspondence, based on a simple observation saying that, oh, look, if we have, these are the green atoms, these are in the austenite phase. If you have two unit cells of the austenite phase side by side, then you can see that there is almost already a BCC unit cell. Well, it's not BCC, it's in fact tetragonal. But based on this, Bain assumed that there was a specific crystallographic orientation relation between the austenite and the ferrite cube. Later on, this was more refined, because Bain is only an approximative description, and this was more refined into what is now known as the Nishiyama-Wassermann orientation relation, or the Kurdyumov-Sachs orientation relation. Actually, the KS orientation relation is the most commonly adopted orientation response for low carbon steel. And KS, Kurdyumov-Sachs, tells you that the 111 FCC plane, so this is this plane, is parallel to the 001 BCC plane. So this is in FCC, this is in BCC, but you can see that the planes are parallel, and that the 111 FCC, this is the close packed, this is the 101 FCC plane, this is this plane, is parallel to the 111 BCC direction. Sorry, I said plane, I meant to say direction. So actually this means that the close packed planes in FCC and BCC corresponds, and the close packed direction of FCC and BCC corresponds also. We will not go into detail. There are many other orientation correspondences described in literature. Now, what I show you here are three 45 sections of steel after hot rolling. And in fact, you can see, in fact, those three steels, they have quite similar textures. The difference between those three textures is not very explicit. There is some differences in strength, but basically they have more or less the same components. Now, nevertheless, the phases are very different. So this is polygonal ferrites. It's a diffusion generated by diffusional mechanism. This is an acicular ferrites, and this is martensite. Martensite is a diffusionless or displacive transformation. By the way, I took this from the reference of Professor Ray, also quite well known in your institute. I think I know Professor Ray since many years, from the time we were working together with Professor John Jonas in Montreal. It was a great time. And you see here that, so what I want to tell you here, that although you have many different, you have total different structures, and nobody will deny that martensite and polygonal ferrites, they are very different. You can see the difference with your eyes closed, so to say, whereas in texture is not so different. So this tells something. This is referring to my introduction when I say, well, we want to know something about the mechanism. The fact that the texture is so similar is an indication of the fact that the orientation relations at the onset of the transformation also are similar. Now, you can apply this in an industrial context. This is old work already from during my PhD, when we investigated the hot band texture that was generated if you roll low carbon steel or even IF steel. In fact, if you roll above if the finished rolling temperature is above the TNR temperature, so that means that all of the hot rolling is done with full interpass recrystallization. So here we have 7 hot band passes, and between each pass, the temperature is high enough and the deformation is high enough so that you have full recrystallization. So what comes out of that is a hot band texture, and you do it completely in the austenite phase. So the AR3 temperature is lower than the finished rolling temperature. So if you do it then we speak of a transformation type texture, and in general is very weak. You see that the maximum is only 2 times random, which is very weak. However, if you do rolling still in the austenite temperature, so the finished rolling temperature is above AR3, but in such a way that the finished rolling temperature is below TNR. So now you do a number of passes, of hot band rolling passes, during which you do not have full recrystallization between the passes. If you do it like that, then the texture totally changes. So you see that the maxima are at different components compared to this. And also it's a much stronger texture. So now here we even have a maximum of 10 times random. Here, these are 2 experimental examples. So, okay. So this it shows you also that by looking at the hot band texture, you can in fact know a little bit, or to some extent, how was the processing of the hot rolled steel. So you can know what was the temperature of the finished rolling compared to the AR3 and the and the TNR temperature. Of course, these temperatures, AR3 and TNR, they themselves are very much dependent on the chemical composition of the steel. Another interesting aspect of looking at a transformation texture is that, as I've said already, there is a fixed orientation relation between parent and product orientations. Parent and product orientation. So actually, this is the equivalence in texture terms, on crystallographic terms, of a kind of a genetic relation between parents and children. So if you, by DNA tests, you can determine whether or not person XY is the parent of person Z. So in texture, we have something different. So, and this we have something similar. So we can use those crystallographic correspondences to determine if you have 2 grains in a product texture, to measure, to gauge, to check whether or not they have a common austenite parent. This is possible. So this allows us to reconstruct the parent phase microstructure at high temperature from a room temperature measured orientation scan of the product microstructure, because of course in steel processing there is we have a huge difficulty, so to say, that we have to address. That is that the overall majority of our experimental observations, they are done at room temperature, whereas a major part of the processing, it occurs at very elevated temperature. So you always have to think back, even if you quench from room temperature, typically you quench from the austenite phase, then austenite phase turns into martensite, and then you say, where I see my martensite in my microscope, there it was austenite before at high temperature. So this, so we can now use crystallography to analyze this a little bit more in detail, and to kind of calculate back the parent phase. So here, for example, we did a test in, this is iron 29% nickel. In this alloy, it also has a austenite to martensite phase transformation, but transformation temperature is about room temperature. So actually, before phase transformation at room temperature, we measure this parent phase, which is austenite. So this is a austenite parent phase EBSD. And in exactly the same site, then we cool down this phase to liquid nitrogen. We heat it up back, and then it transforms from austenite to martensite. And if you heat it then back up to room temperature, then it stays martensite. Okay, so you have have from this texture, you have from this microstructure, you go to that microstructure, and it is the same side. And now we are going to use our crystallographic correspondence relations to calculate this from this structure back to that structure, and then we can compare. So you see, okay, so this is the reconstructed parent phase texture, and this was the original structure before phase transformation. And you see that thanks to this genetic correlation between product and parent phase, we have quite a good match, with exception here of a number of points, and these are twins. The method that we use does not really allow us to resolve twins. So we are working on this now, but yeah, this is still an issue we have to address. Okay, so for example, this was a paper based on a slightly different method published by some colleagues of us. And you see that this is these are back calculated hot band structures from steel. So this is hot rolled steel. And as I said to you, sometimes steel is hot rolled below or above TNR. Above TNR means that you have fully recrystallized structure in austenite and then transformed. Below TNR means that you have only a partially recrystallized structure at high temperature and transformed from the partially recrystallized state. And you can see that by applying such genetic algorithms, we can back calculate the original structure. So this was the structure that existed in the steel at the high temperature just before transformation. So you can see on the left-hand side, the steel was definitely not fully recrystallized because you have these long elongated grains, whereas the steel on the right-hand side was recrystallized because you have more equiax grains. Now so now I've spoken about phase transformation. Let's turn our attention now to plastic deformation. So actually, probably you know this already, but just I remind it that if you have a shear, you know that on the crystallographic level, all plastic deformation occurs by slip, either dislocation slip or by twins, but by slip. And invariably, this slip, this also, if you want to accommodate a macroscopic strain mode, we know from experience that metals are quite plastic. You can mold them if you have force enough in about every shape that you like. Well, as a result of this plasticity, not only the shape of the crystal will change, but also its orientation will change. So its orientation will change, and you have a formation of texture. If the orientation of the crystal changes, and if this occurs for many crystals at the same time, then it is you have a formation of a example with a random texture. After an amount of deformation, you will generate a certain texture. And of course, it's very interesting. So we want to understand this, how texture changes during plastic deformation. And we did an experiment. This was a commercially pure aluminium. So now we switch to aluminium. These are the three other sections on aluminium. We measured an EBSD of about 800 grains. And you can see this is a cube component. So in the 5 to 45 degree section, we also have a copper component. This is this is a cube component, and this is a peak component. Okay, so we did an experiment in which we rolled this aluminium 6, 12, 18, and 24% in successive passes. It would be nice to say, what we really wanted to do is to make ourselves very small and to walk around in the crystals of that material while it is being rolled. Of course, that's not really possible. So that's why we had to design what is called a near in situ experiment. So we made a very small sample which we embedded. This is our sample, which we cut into two, okay? And then we embedded it into a sample holder, and all this thing was rolled together. And after each rolling pass, we dismounted the sample, we disassembled this sample, and we looked at this cut edge here. So this is shown here in this video. Can you see the video?
Yes, sir, it is visible.
Okay. So you see between each rolling pass, we opened up the sample, and then we looked with into the electron microscope with EBSD, and then we put back the sample together and we did the next rolling pass. So in small passes of 6%, we went from 0 to 24% of rolling. And this is the result, then what you see. So now you see how the grains deform during rolling. Okay. So I have to thank my colleague Hari Pergazi for this. It was part of his PhD work. It was a very elaborate experiment. So mind you, this is not an animation. This is not a cartoon. This is the real experimental behavior on how the grains rotate. And you can see two things. First of all, the grains, they change color. If you have an initial grain, after some amount of deformation, it has changed the color. So that's because the crystal rotates. The color here means crystal orientation. Not only that, there is a second important thing that you can observe, that is that there is a gradient of colors appearing. Originally, all these grains, they had more or less, they had a uniform color, they had a uniform crystal orientation. And after some while, you see that there is an internal grain gradient. So this means that the orientation splits up, in fact. It's not a homogeneous orientation anymore. Now, we can, well, I can give an entire presentation about this experiment. I don't have time to go into the detail now. You can see here that we model this behavior by what is called the Taylor model of simulation. And in fact, we understand this quite well. If you see this is after 6, 12, 18, 24%, the model texture resembles on average quite well the experimental texture. However, individual grains may show a total different behavior. Not all of them. So here, these are for single grains. For example, you may have here a grain that, so the black path is the experimental behavior and the red path is the model behavior. For some grains, it corresponds very well. For other grains, that not at all. You see that here there is a big difference. Also here there is quite a difference. So there are many reasons why there may be some deviations. I'm not going into detail. Another thing is that some crystals after deformation, they stay more or less homogeneous. So initially you always start with one single point. So these are all the points in one grain. So they are very closely clustered. And after deformation, these points, they spread out. You have a scatter. This is not a measurement error. This is a real effect. So here in so-called high Taylor factor grains, we may have a scatter of more than 30 degrees. So inside grain, you have the appearance of orientation scatter of more than 30 degrees. You also have what is called, sometimes you have these high angle grain boundaries appearing. And this is really the process of plastic deformation generates high angle grain boundaries. So you have grain refinements. This has given rise to the process of probably some of you have heard already about it, severe plastic deformation. Actually, in September was planned the Nano SPD conference in India by my good colleague, Professor Satyam Suhas. But unfortunately, this also had to be delayed because of the COVID crisis. I have another example. This is what is called an oligocrystal. These are very huge crystals, and so these are actually millimeter-sized crystals. This is a iron 3% silicon. This is in the middle of a tensile test. We did a tensile test in the scanning electron microscope, and this is what you see. You see how grains fragments. You see that's how new grains arise. Okay. Here, for example, you have a new grain boundary. Here you have shear bands arising from the grain bound. This has to do, of course, with the fact that the plastic deformation of one grain, it is not exactly compatible with the plastic deformation of the neighboring grain. And this gives rise to these accommodation at grain boundaries, to intense formation of shear bands and what we call strain heterogeneities. Also here, for example, you see a drastic split up of grains. You can see this here, how in the end you have different crystal orientations arising. So let's finish now with the texture induced by recrystallization. And this is an image which is typical for steel industry. All people in the steel industry, for example, if you deal with IF steel, know this very well. So this is the just a cold rolled steel with different levels of cold reduction, 75, 79, 83, 87, and 90%. So you have a typical alpha gamma texture, and these texture become stronger. So here we have a maximum of 1, 2, 3, 4, 5, 6, 7 levels. 1, 2, 3, 4, 5, 6, 14 times random. So this is already quite a strong texture after rolling. If you now anneal this texture, then you get this. You don't get an alpha gamma fiber texture anymore, but we get this gamma fiber texture. Remind you that in the beginning I said that this is the texture that you need for good deep drawing properties in steel. So this is very important if you make car body panels. Car body panels is one of the most notorious widespread applications of steel sheet manufacturing, and then you want exactly this type of texture. And you see that it's a gamma fiber, although it's not a perfect gamma fiber. There is some kind of curvature in here, and also at a higher reduction, the texture becomes stronger, but it also becomes less and less homogeneous. Here it's still more or less homogeneous on the gamma fiber, whereas here you have a strong maximum on this component, which is the 111, component. Okay. So, and this has an effect on the R value. This is a mechanical property. It's the R value. It is the width to thickness change in a tensile test. So if you do a tensile test, so actually for good deep drawing, you want that all the extension is accommodated by width change, not by thickness change, because thickness change will increase the risk of fracture. So, and you see that if you have, depending on the rolling amount of rolling, the R value profile, this is the R value measured on different tensile test samples that enclose different angles with respect to the rolling direction, going from 0 to 90 degrees. And you have different profiles, and this is quite important for the application of the steel. So by controlling the texture, you can in fact control the R value profile by controlling the rolling reduction. This was an example that I gave you, typical from industry. Now you also can do other things with steel. This is, for example, this is not cold rolled steel, but this is hot rolled at quite high temperature, around 1000 degrees C, reheated to actually the rolling temperature was a bit lower. It was hot rolled from 220 millimeter to 10 millimeter. And this steel has a high silicon content. So at this temperature, it is fully in the ferrite region. So we measured a very huge EBSD. You see here, this is 2 millimeter. And this is the texture that you see. So this is obviously, it's a recrystallization texture. This is not a gamma. The gamma fiber would be here. This is a cube fiber. It's an entirely different fiber. You see this? So this is an entirely different fiber by rolling at elevated temperature. So we also try to model these fibers, but I don't have time. So there is something like the Taylor factor. The Taylor factor is an important theoretical quality. It tells you the energy, the instantaneous power dissipation, in fact. So for each crystal orientation, we can calculate the Taylor factor, and this is a Taylor factor map. This is not a texture, it's a Taylor factor map. So blue means that these are the crystal orientations with low Taylor factor. It means they need they need lower energy to be deformed. Whereas red means just the opposite. These are crystal orientation with high energy. They need a lot of energy to be deformed. And you can see here that there is a clear correspondence between the maxima of this texture. This is the observed texture. So see the maxima and the blue areas. So it means that the low Taylor factor grains have been selected for recrystallization. So this also remains valid under more exotic conditions. This is asymmetric rolling, but I don't have time now to go into detail. But also in this case, holds the correspondence between the blue areas in the Taylor factor map and the low and the maximum of the ODF. Okay. Just to end my presentation, let me show you something. So this is a phenomenon which is described in the literature as a texture memory. Suppose you have a a material, this texture, gamma fiber texture, with a maximum here, 111,112, and you anneal this at elevated temperature in the full austenite range. Now you have to know that normally you would see the KS orientation relation, the Kurjum of Sachs, but for each parent orientation you have 24 possible variants. Okay. Yeah, you have 24 possible variants. So if you go from the room temperature ferrite texture, you go somewhere at high temperature in austenite. So each crystal can transform to 24, each parent crystal can transform to 24 product crystals. And then you transform back, and again you have a 24 multiplication. So 24 square is 576. So actually what you would expect then is to have a more or less random texture, because you have a tremendous weakening from each single crystal. If you would do this with a single crystal, according to this line of thought, you would end up with 576 crystals, all of different orientations. So a single crystal, of course, has a very strong texture, and then you end up with a very much weakened texture. Now, what you actually see in reality is not that. You're very surprised to see that if you do this experiment, like we did it, actually the product, the final texture, is almost the same than from what you start. So this is something what we call texture memory. It is as if this whole path that you do, the material remembers in one way or another, each crystal remembers its history and returns back from where it came. So this is a mystery. Nature has many of this type of mystery. If you have the migrating birds, for example, they also know exactly where to go back to from where they came. So how comes this? There must be a mechanism. And we have done a lot of research on this, and we came to a definite conclusion that actually because the essence of the story, I'm going just to tell you the essence of the story, is that nucleation of the new phase always occurs at the grain boundaries of the parent phase. That's by far the most preferred nucleation side. There are good thermodynamical reasons for that. So actually, if you have two austenite grains and you have a ferrite grain forming here, in the most general case, the new ferrite grain will have a Ks orientation relation, not with both grains, but only with one grain, with one neighbor. Now, in a very small amount of there are a minority of austenite grain boundaries, gamma 1 and gamma 2, that are by coincidence misoriented, such that the product orientation relation, the product grain, the ferrite grain, can have a Ks orientation relation with either side of the boundary. We call this double Ks. So this is not possible for the general random high-angle austenite grain boundary, but it is possible for a small minority, in general 5%, of special austenite grain boundaries. And it is this mechanism that is responsible for, in the end, texture memory, because that's how the material remembers how to go back from the to the initial orientation from where it started. This is not only a theoretical model that we have published, but it's also backed up by very well documented experimental data that we also have published in ACTAMAT. So this brings me to my conclusions. I've written here 4 conclusions. That actually texture study in materials science, it is essentially a quantitative statistical study of crystallographic phenomena that contributes to the shaping of microstructure. Because, excuse me, everything what I've shown is statistically backed up. So a texture is never made up by one single grain. A texture is made up by a distribution function, a statistical distribution function. And this is, in fact, a very important aspect of metallography. Microstructures are essentially statistical data. And texture allows us to deal with this in a very good quantitative way. So my second conclusion is that it filters out the relevant crystallographic orientations that appear in solid-state transformation processes occurring during making and using of materials. So if you measure the texture, you find the certain orientations will be preferred, others not, and this has a reason. And the reason for this is the metal physics. So in my third conclusion, I reiterate that detailed study of the texture provides a major gateway to a better understanding of the complex mechanisms involved in various phenomena, such as phase transformation, plastic deformation, recrystallization. And then I've backed up also my story with a number of typical examples in which the knowledge of texture can help us to obtain metal sheet with better mechanical properties. Thank you for your attention, and of course I'm very much ready to answer.